Hi, this is Arindam from the School of Chemical Sciences, NISER Bhubaneswar, and welcome to the lecture series on the hydrogen atom problem. This is lecture 2 of the series. As always, let's start with a recap of whatever we have done so far. We started our discussion in lecture 1 with a proof that a two-body problem can eventually be converted into an effective single-body problem if the potential that acts between these two particles are a function of their separation only. It means that if the potential can be represented using this internal vector small r, in that case, the motion of the two-body problem can be split into two parts. One is the motion of the center of mass, which is equivalent of the entire system moving together, which is not so important or not so interesting for an hydrogen atom problem. We have discussed that in lecture 1. And another one is the movement of one particle with respect to the other. So let me also comment on a particular question that my students often ask at this particular juncture, is that uh, this claim that we are converting a two-body problem into a single-body problem, how is that been achieved? Because they get confused that when we start with a two-body problem, say we are starting from M1 and M2, and then we convert it into another two-body problem with capital M and small this mu, correct? So capital M is the total mass, mu is the reduced mass. Originally we had M1 and M2. So we earlier also we had a two-body problem. Now also we had a two-body problem. So how come this is a single-body problem? The single-body problem will happen if we somehow not interested to monitor capital M. Monitor capital N means that this capital M is basically an hypothetical particle which is basically the center of mass. So now if we are not interested to track down the center of mass, that means we are not interested to track down the entire system as a whole moving in space, then we are only interested to track down one particle with respect to another, and that can be tracked down by this another hypothetical particle having mass mu, and in a reference frame of this particular kind, where the one is fixed because we just need to understand the relative motion of one with respect to another, so we can fix one and then we can simply monitor a single particle, and then it will ultimately become effectively one body problem. Additionally, we argued that as the nucleus is heavier than the electron by this large factor, we can approximate as if the nucleus is infinitely heavier than this electron. In that case, we ignored all motion of the nucleus and we assume that the nucleus is fixed in space. And if we assume that, then we can redraw our coordinate axis such that the origin is now coinciding on the nucleus. And in that case, the motion of the electron can be represented by this internal vector r, which is going to be acting as the position vector for this electron. We can write the potential that is acting between this two charged particle is in this particular format. This is the Coulomb potential. We also formulated the force that is acting between them, and the force that this electron is experiencing due to this positively charged nucleus is obviously in this particular direction. It is an attractive Coulomb force. And also we wrote down the total Hamiltonian using this form of the potential, and we showed that this particular Hamiltonian in spherical polar coordinates can be split into three parts, each containing only one variable. And in that particular case, as it is the case always, that the solution to the differential equation, the the Schrodinger equation can be written in terms of three different functions, each function having only one variable in this particular product form. We also derived the three differential equations that would ultimately give us these three functions. And here are those equations. So we got this equation for the phi, equation for theta, and equation for capital R. And also we discussed the procedure that we'll be solving first, the first equation, and you will find that only certain values of ML will give us quantum mechanically acceptable solutions. We'll use those ML values in this particular equation. Then we'll solve this second equation. We'll find that only few allowed L values will give quantum mechanically acceptable solutions. We'll be using those L values here, and finally we'll solve this equation. And from these three equations, we'll be getting the phi, the theta, and the R, along with allowed values for L and ML. So let us start lecture 2 with the solution of the first equation. The equation for phi is a second order homogeneous equation with constant coefficients. We have already assumed that ml square is a constant. If we compare this equation with a general homogeneous second order equation with constant coefficients, we find that a equals 1, b equals 0, and c equals ml square. That directly gives this important factor b square minus 4ac as minus 4 ml square. Now, as ml square is definitely a positive quantity, this whole thing becomes negative. And we know that if b square minus 4ac is negative, then we get a complex conjugate roots, and the roots are going to be plus or minus iml. We can use either of them. Really doesn't matter in this particular case. So let's try the solution phi is equal to e to the power I ml phi. Now, as this variable phi is a periodic variable, it is the range is 0 to 2 pi, and any acceptable quantum mechanical wave function should be single valued for each and every value for the variable. This boundary condition comes into place automatically. So once we have a full circle of phi going from 0 all the way to 2 pi, the value of this function should be same. So that means that the phi at 0 should be equal to phi at 2 pi. And if we just impose that condition into this particular function, we immediately get e to the power I ml 2 pi is equal to 1. Means that the cosine part has to be 1 and the sine part should be 0. And this is possible if this ml is restricted to take only integer values. So therefore we get only a few allowed values for ml, and those values are ml mod can be only either 0 or any of these integers. There is no upper bound though. It can take any integer values all the way to infinity, but nonetheless it cannot take any value other than integer values or the value 0. So we have finally got the solution for the function involving capital phi. The solution is of this form, where the ML now has a condition that it cannot take just any values, it has to take integer values. So the mod of ML is 0, 1, 2, 3, etc. There is no upper bound though. Or we can write down ML takes the value 0, plus minus 1, plus minus 2, plus minus 3. Either way we can represent it. But nonetheless, the phi part has this particular form of solution. Now let's go to the second equation involving the variable theta. So the equation involving theta is definitely not as simple as the equation involving phi, particularly because we do not have here constant coefficients. We have coefficients which are function of the variable. So what we'll do as a first step, that will be taking a simple substitutions which will give this equation a different look. Uh, then we'll solve that equation. So let's take that substitution. So we will take the substitution cos theta equal to k, which will give us dk as minus sine theta d theta. We can also write in this form d dk is equal to minus 1 over sine theta this time d d theta. We'll be using this particular form, that 1 over sine theta d d theta with a minus sign is here. So we'll replace this entire thing by just a simple d dk. Also, if we multiply sine squared theta both sides, or minus sine squared theta both sides to be precise, we get sine theta d d theta here. And from the left hand side, we get a minus sine squared theta d dk. Again, the sine squared theta is just 1 minus k square. So we finally get the sine theta d theta is equal to 1 minus k square d dk, with this negative sign obviously. And we'll be substituting this particular form, sine theta d d theta. Here we have a sine theta d d theta here. So we'll be replacing this entire thing here. So we'll be doing this two substitutions in the original equation. And obviously the sine square theta is going to be 1 minus k square. And then we'll have this same equation, a slightly a different look with the variable now k instead of the variable theta. So with the substitutions k equals cos theta, the equation involving the function capital theta takes this particular form. If we do not like this negative sign at the beginning of the equation, we can take a global negative both sides. The right hand side is 0 anyway. The left hand side will simply switch its sign. This part is going to be positive, and these two terms are going to be flipped over. We will, however, not solve this equation, which we should, but rather we will be solving this equation, which is related definitely to the original equations. We can see that the first term is same. The only difference is that this particular factor is missing from this equation. Now the question is that what's the reason that we will be solving this one instead of the original one? That this is easier to solve. That's okay. It's easier to solve, so we'll solve this. But now question is that how justified it is. The justification is that the solutions are related. So the solution to the original equation A is this theta. Theta is the function that we want. This is part of the grand solution for the hydrogen atom problem. But the solution to this equation, which we are going to solve, is this PL, right? Now, obviously, this equation has two constants. One is L, another is ML. That is why the solution, I have written down L and ML both as a subscript to just show that although K is the variable, this theta, the function, parametrically depends on both the constants. Whereas in this particular equation, we do not have ML, we have only L. So I have written down this P, the function P, parametrically depending on L, but the variable is still K. So now let us go and solve this equation first. Once we get the solutions, this P, the function P, which is parametrically depending on L, we'll plug that particular solution to this equation, and then we'll get our theta back, which we finally obviously want. If we perform the first derivative, we can write the same equation in this expanded form, which clearly shows that this is a second order differential equation, homogeneous definitely, but not with constant coefficients, because the coefficients are function of k. So we'll adopt the method of power series solutions. We'll assume that uh, the solution PL is an infinite power series of this form. Now, if we use this form and we plug in this value of PL into the equation, we get this, right? So for example, this 1 minus k squared is directly coming from here, and then we have a double derivative on PL. So if we take 2 times derivative of this series with respect to k, we get j and j minus 1 coming down with aj the coefficients and k j minus 2. Similarly, with a single derivative, we have only j coming down and then k j minus 1. And this part remains intact. And we can now quickly see that, well, there will be only two different powers of k remaining, because if we multiply this k squared term with this part, correct, this k j minus 2, k to the power j minus 2 will come back to k to the power j. And if we multiply this k to this series, then again here also the power will be k to the power j. We already have k to the power j here, but if we multiply this term 1 to this particular series, then we have k to the power j minus 2 remaining. So obviously only two different powers will be there. One is k to the power j and one is k to the power j minus 2. So if we just combine all the terms of k to the power j coming from here and here and here together, we get this common coefficient. That is exactly the thing that I have done here. So this is the final form that we will be obtaining if we use this power series form of the solution PL, and then we plug in this thing to this equation. So the relationship we have got so far is this, and on a first glance it might seem that there are two different powers of k present here. One is k to the power j minus 2 and another is k to the power j. But a closer look will reveal that the j equals 0 and the j equals 1, both of these two values of j will not give anything non-zero from this particular part of the series. The first non-zero term that are going to be there from this particular part of the series is the following. We can write it down. So it comes with j equals 2. So this is 2 multiplied by 1 multiplied by, this is a2 because j equals 2, and then k to the power 0. So this is the first term. So the same thing can be written down with the change of index from j to I. The difference that has been done is that it has been written in a slightly different way. But if we check, the same term will come here as well as the first term. The difference is that this particular series will start from I equals 0 itself. So now if I just take I equals 0, then we get here, from here it is 2, I equals 0, so it is 2 multiplied by 1, this is 1, then multiplied by a2, correct, because I equals 0, and then we have k here taken common out, so I equals 0, so it's k to the power 0, right? So we can write it down the k to the power 0 as well. That's the first term. So we can get that these two series, so this one and this one, they will give the exact same terms. The only difference is that here in this particular I series, I have this particular k to the power I taken common out, and that is key to the next statement that I'm going to make. And the statement is that if this infinite series has to be equated to 0 for each and every value of k. Now what is k? K is cos theta. We have defined it that way, and theta can take any value. So therefore k will be running from 1 to minus 1. It can take any value. So if this left hand side has to be equated to 0 for each and every value of k, there is only one way, that the coefficient that is written underside this bracket, the coefficient for each power of k, that means for each value of I, this coefficient should be 0. So when we equate this coefficient of k to the power of I for each I, to be 0, we'll get our recurrence relationship. So we have got our recurrence relation by equating this factor to 0. Clearly it is connecting AI to AI plus 2. So we'll be getting two independent series. A0 will give to A2, then A4 and A6, and then A1 is going to give it A3, A5, and A7. So this is very similar to what we obtained for the simple harmonic oscillator as well. We had two independent series. A0 and A1 being the two independent constants. So these two constants will ultimately decide the amplitude, the global amplitude of the theta part of the wave function. But nonetheless, we have two independent series, and they are related through this recurrence relationship. Now, the next step in power series solution is that yeah, we need to check whether this infinite series with this recurrence relationship gives us an acceptable solution. By acceptable, I mean quantum mechanically acceptable solutions or not. So for that, what we need to do is we need to check how the behavior of the series becomes when infinite number of terms are kept. So the procedure is that we will be taking the ratio of AI plus 2 over AI, which is eventually this particular factor, for I tending to infinity. So when we really have a large number of terms in the series, that is when this index I tends to infinity, what we get is this L into L plus 1 becomes much smaller with respect to I multiplied by I plus 1, because L is a constant and L is a small number, as we'll find later. We can also ignore this 1 with respect to I. So this numerator becomes just I square. The denominator is a straight I square. We can ignore 2, we can ignore 1, and this is I square. So therefore, AI plus 2 over AI for large I becomes simply I square over I square is equal to 1. What does it mean? It simply means that consecutive coefficients of the series when you have large number of terms become equal. They're same. It is saturates to a particular value and it just keeps repeating. Now the question is this a good thing or a bad thing? It turns out to be a bad thing for us in this particular situation, because k is equal to cos theta. That is how we have defined it, correct? Now cos theta can take value plus 1 to all the way to minus 1. It can take any value depending upon theta. Now when k takes the value either the plus 1 or the minus 1, then this particular fact that ai plus 2 is equal to I, whatever the value of I it is, an infinite series with k equals 1 simply means that we are keep adding the coefficients, and now the coefficients are repeating. AI is equal to AI plus 2. So any particular value of AI for a large I, that will be keep repeating infinite number of times. And we know that no matter how small a number it might be, if we keep adding the same number infinite number of times, it will ultimately lead to infinity. So as k can take actually values for 1 and minus 1, for fractional values, the scenario is different. But as k can also take values plus 1 and minus 1, a situation like this, ai plus 2 equals ai, is not good for us. It simply means quantum mechanically we cannot have an infinite series as our theta function, although we have got it. What's the remedy? We know the remedy from our discussion in simple harmonic oscillators. The series is probably not an infinite series. The series is getting truncated after only few terms. Now let's check what can make this particular series get truncated after only few finite number of terms. The series is going to be truncated after only certain terms if this particular quantity, which is the ratio of ai plus 2 over ai, is 0 for certain values of I. Now I is an index. It can take the value 0 or it can take only integer values. So this particular quantity will be 0 only if this numerator is 0, and that will happen if I restrict L to take only integer values, because in that case only I multiplied by I plus 1 minus L multiplied by L plus 1 is going to be 0 when I is equal to L. Let me take an example. So suppose L is equal to 5. So then when I will become 5 in the series, we get A7 is equal to 5 multiplied by 6 minus 5 multiplied by 6, because both I and L are 5, divided by 7 multiplied by 6, I plus 2 and I plus 1, and A5, because I equals 5. So this is equal to 0. So this means that we get A7 is equal to 0. Now A7 equal to 0 directly means that we get A9 equal to 0 as well, and therefore A11, A13, A15, all the odd coefficients beyond A5 are all 0. So the odd series is truncated at A5. That means k to the power 5. That is the fifth power is the highest power in that particular series, odd series. The value of L equals 5 because it's an odd value. That is why the odd series gets truncated at the fifth power. But the even series will simply go on, because in the even series, we start from A0, that gives me A2, that gives me A4, that gives me A6, and then A8, and then A10. Nowhere in between I get the 5, correct? So this L equals 5 will not stop this particular even series, because I will never take the value 5 in the even series. So if we have to stop the even series, we have to stop it by making the starting point 0 itself. There's no other way. So therefore, we need two conditions to work simultaneously. First, either A0 or A1, any one of them is going to be 0. Which one is going to be 0? That depends on which value L takes. If L is even, then A1 is 0. If L is odd, then A0 is 0. And L cannot take any other value other than integers or 0. So far we knew that L is just a constant. Now constant can be obtained by any value of L. There is no need that L has to take only integer values. In fact, L equals 1/5 also gives L into L plus 1 as a constant. But now we see that in order to make the theta portion of the hydrogen atom wave function, we need to restrict L to be taking only integer values. Otherwise, this series is going to be a truly infinite series, which will diverge to infinity when k will take the value either plus 1 or minus 1. So let's summarize the two conditions that we have just got, which will make the theta function an acceptable function quantum mechanically. So here is a list of all the conditions that we have just discussed. We have A0 equals 0 or A1 equals 0. So both the odd and even series will not exist simultaneously. L can take only integer values, and A0 is 0 when L is odd, so that the even series is truncated at the very beginning, and the odd series will truncate when I becomes equal to L. And the AA1 is 0 if L is even. In that case, the even series will get truncated when I is equal to L, and A1 equals 0 will make the odd series not even starting. So let us take few examples for a few initial values of L, and let's check how the PL, which are a polynomial of degree L, look like. So I have written down a few cases for a few initial values of L, 0, 1, 2, 3, and I have noted down which series is absent. So when L equals 0, A1 equals 0, so the A0 series remains there. And as this is L0, so k to the power 0, which is 1. So this is a polynomial of degree 0, means it's a constant, and that constant is A0. Then we get L equals 1. This is an odd number, so therefore the even series has to be 0. So the A0 is equal to 0. And the highest degree is 1. So that is this k to the power 1k. So the A1k. Then it is 2, and again A1 is 0. So this is A0 1 minus 3k squared. And these are the different PLs that we get. We can just take one example how these coefficients like -3 or -5, these coefficients are calculated. So let's take a simple example. So we have this our recurrence relationship. Let's take L equals 2. That means this particular case L equals 2, A1 equals 0, and then we would like to calculate A2 from A0 so that we can take this A0 common out. So we have L equals 2, and if it is A0, then I equals 0. This I equals 0. And if I just plug in the value of I equals 0 and L equals 2, we get a -3. And therefore A2 is -3 times A0, and that is exactly what I have written down here. So this is A0 minus A2k square, because this is k to the power 2, so it is A2k square. Now A2 turned out to be -3A0, so you can take A0 common, and then it becomes just 1 minus 3k square. Similarly, you can just keep on calculating the different coefficients from A0 or A1, depending upon whether it's an even series or an odd series, and you can write down the entire polynomial for PL, which is going to be a polynomial of degree L. Just one side remark before we further go ahead is that these polynomials, they have a name. They are very well known, famous polynomials, and they are called the Legendre polynomials. The Legendre polynomials are coming because we have taken this L now to be integers. So if we just quickly check the original differential equation from which this polynomials came, subject to the condition that L can take only integer values, we'll see that this differential equation is just the differential equation that gives the famous Legendre polynomials. So here is the differential equation that generates the Legendre polynomials. Those are polynomials of degree n. It depends on which n we take in the differential equation. N can take the values 0 or any positive integers. So this is the equation that we also obtain while solving the theta function. When initially we started solving the theta function, we did not have any restriction on what value this L can take. We had L into L plus 1 here instead of n. But the moment we found that L cannot take any value other than integers, because it has to match with the index I, which can take only integer values, we actually obtained this equation. And the solution to this equation is known for ages. So this is the Legendre polynomials, and that is why we got Legendre polynomials as constituting polynomial for our theta function. Now, I started this discussion with the mention that the Legendre polynomials are not actually the theta function. The theta functions are related to these Legendre polynomials. In fact, the theta function that we'll be obtaining, they also have a name. They are called associated Legendre functions, and the relationship is already known. So let me write down the relationship once again. So here we got the relationship between the Legendre polynomials and the associated Legendre polynomials, and they're related in this particular fashion. This part, the left hand side part, is the theta function that will constitute finally one part of the space wave function for hydrogen atom problem. But we'll first get the Legendre polynomials for a certain degree, depending upon what L we choose. We can then differentiate it certain number of times, some ml mod ml number of times, and then we can get this function. As we know that k is equal to cos theta, we can write down this entire equation in terms of now cos theta or sin theta as well. So if we do that, the same equation look like. So we have got this 1 minus k square is simply sine square theta. With this half here, sine square becomes sine, and so therefore this whole thing become sine to the power mod ml theta. And well, this k is a cos theta here, but then it has to be ml times differentiation. That is exactly what I have written down here. PL k becomes PL cos theta, and this is the relationship. So this is the finally the expression for theta that you have got. But one important thing is now, as this is the expression that we have got, and we know that PL is a polynomial of degree L, we get certain restriction on the value of ml that it can take. We know that a polynomial of degree L can be differentiated at max L times before it becomes 0. For example, if we get if we take a polynomial of second order, y is equal to some ax squared bx plus c, we can differentiate it once, it becomes 2ax plus b. We can differentiate it two times, then it becomes 2a as a constant, and if we try to differentiate it once again, it will become 0. So a polynomial of degree 2 can at max be differentiated twice or two times before it becomes 0. Similarly, for a particular value of L, PL is a polynomial of degree L, so therefore it can at max be differentiated L times before this whole thing becomes 0. We do not want this whole thing becomes 0, because otherwise the theta function is going to be 0, and we know the hydrogen atom wave function is a product of the r part and the theta part and the phi part. If the theta part becomes 0, then the whole wave function is going to be 0. That is meaningless for us. So therefore we get an upper bound for the value of mod ml, and that is L. So what we get is that the mod ml will be either less than or at max equal to L. So let's see what's the range that we get with this particular condition. So as mod ml can take the value at the most L, so we get the values allowed for mod ml as 0, 1, 2, 3 all the way to L. L is an integer, we already know that. In other words, ml will take the value all the way from minus L to plus L with a gap of 1, because ml can take only integer values. That also we know. So at the very beginning, when we were solving the phi equation, we found that mod ml can only take integer values, although we did not know any upper bound for that. After solving the theta equation, we found that L has to also take only integer values. There is no upper bound for L at this moment, but we got an upper bound for ml, or rather the mod ml, that is an upper bound is the L, and therefore the acceptable values of ml becomes minus L to plus L with a gap of 1. So now we have got already two solutions with certain conditions on these ml and L, these constant. These are basically our quantum numbers. These are going to be defining the state and the energy finally. So these are quantum numbers. So we have already got two of our quantum numbers. One is ml, another is L. Both of them take only integer values. ml can take values depending on L. At this moment, we do not really have any upper bound for L or any restriction on L other than the feature that L can take only integer values. So let me simply write down those two equations or those two solutions that we have got in this lecture 2, and then I'll end the lecture 2 here. In lecture 3, I'll start solving the radial equation, that the R part, and then after we get all three parts together, we'll constitute the whole wave function for the hydrogen atom. So here are the two functions that we have obtained so far. The phi part, which depends on ml only. So I have just give a subscript ml. This is this particular form. e to the power I ml phi. Ml can take 0 plus minus 1 plus minus 2 all the way to plus minus L. We know that now. And the theta function has this particular form. The PL cos theta are the Legendre polynomials. We can just plug in a particular Legendre polynomials of degree L, and then we can take the differentiations required to reach up to theta. We have L equals 0, 1, 2, etc., etc. ML can take, depending upon what L we take, certain values. So we'll get a series of values of theta and phi depending upon what L value and what ML value we take, thus these two quantum numbers. That we'll be discussing later, this combinations of this L, ML, etc. So let me just conclude this lecture here, and I'll see you in lecture 3 on the hydrogen atom problem.